section 9.6. I think it's the last section. So looking at how to find perpendiculars, or the shortest distances between two straight lines, or from a point to a given line, or a point to a given plane. That's what we're going to consider. So if you've got two straight lines, obviously your two lines could be parallel to each other, and then the shortest distance always makes a right angle to both of those lines. So this is going to be your D min, if you like. That's the shortest distance. That's a perpendicular distance. It's going to be perpendicular all the way through. Now if you've got two skew lines, so this is where you've got two lines like that, then if you consider shortest distance, I mean, you've got lots of perpendicular distances, but we're normally interested in finding one of those distances which is going to be perpendicular. Now, it's hard to draw it in 2D, but you need to imagine that these two angles are right angles, so they're not parallel and they don't intersect. Okay, so this is going to be D, possibly D min if the shortest distance is considered. Point to a line, so you might have a straight line and then you've got a point. So there's a point P. Now the shortest distance is not going to be this way, it's not going to be this way, it has to be a right angle to the destination. Okay, so this is D min. That's perpendicular distance. It's also called shortest distance. So perpendicular distance to L is also the shortest distance. And point to a plane, so okay, so that point P, what we're going to use, what fact we're going to use when looking for that distance, perpendicular distance, again will be the shortest distance. This is for both of these. This is the distance D that the line with the passing through P and it's perpendicular to the plane, the point of intersection of that line with the plane. So this is the direction vector is going to be the normal vector to the plane. So it's going to be R equals P plus let's say T N, and then you find that distance by finding the point of intersection and then distance. But there is a formula that you can use as well if you've got the equation of that plane and the coordinates of that point. You can just use the formula which is in the formula booklet, so you'll be introduced to it in a minute. Okay, so let's have a look at example 24. So you've got two straight lines, and we're going to show that obviously we are told, I think, that they are, well, we could see that they are parallel because the direction vector is the same, and we're going to show that the distance between those lines is 21 root 2 10. So so in those questions, best thing to do is always do a little sketch. So you've got two lines, L1 and L2, and let's think about a couple of points on this line. Though because we don't know which points will be right opposite each other, so that the distance between them is the shortest distance. So what we're going to do, we're going to express point A in terms of the general point of the straight line. So 1 plus 5 lambda, and this is 2 plus 4 lambda, and then minus 1 plus 3 lambda. and do the same with B. So it's 2 plus 5 mu, and then 4 mu, 1 plus 3 mu. And what do we know for certain? If we're looking for the shortest distance, so the distance between these two lines, we are going to consider perpendicular distance. So we know that vector AB is parallel to the direction vector of line A1, or you could have picked the line L2 as well, but I'm going to just, it's enough to show that it's perpendicular to L1 and use that information. So what's AB? Well, AB is this vector 2 plus 5 mu, 4 mu, 1 plus 3 mu, subtract 1 plus 5 lambda, 2 plus 4 lambda, minus 1 plus 3 lambda. So we've got 2 minus 1, which is 1, and then you've got plus 5 mu minus lambda, and then you've got minus 2 plus 4 mu minus lambda, and then we've got 1 plus 1, which is 2, plus 3 mu minus lambda. Now what you can do, because when they are parallel, these are just they represent another, you know, constant, so you could say let t is equal to mu minus lambda, just so you don't need to write it down so much. 5t minus 2 plus 4t, and then 2 plus 3t. There you go. We're going to now do the dot product, because since AB is perpendicular to direction vector 5, 4, 3, that means that AB dotted with 5, 4, 3 is equal to 0, because that happens for 90 degrees and cos 90 0. So let's dot this vector with 5, 4, 3. And you should be able to solve it and get a value for t, and that will give you a way of working out the distance. So you've got 5 times 1 plus 5t plus 4 times minus 2 plus 4t plus 3 times 2 plus 3t is equal to 0. Now, if you solve this, you should get 25 50t 5 minus 3 plus 6, so that's minus 3. There you go. Now that gives me the value of t that will enable me to work out AB. So let's sub it into AB. There you go. That will give me, so you can sub it in using a calculator. The values you get will be 35 over 50 minus 112 over 50, 91 over 50. There you go, that's my AB. But you've been asked to show that the distance is 21 root 2 over 10. So let me just, I'm trying out the paper here. Yeah, that will do. So all you need to do is use quick Pythagoras. So AB is going to be equal to 35 over 50 squared plus 112 over 50 squared plus 91 over 50 squared. The square rooted, put it into the calculator. This will be 21 root 2 over 10, shown or proven, if you like. There you go. So this was example 24. Moving on to example 25. This time we've got two lines and we have to find the shortest distance between these two lines. So we are going to assume that they don't intersect. We haven't been asked to show that they are skew lines, but they will be either parallel, which they are not, or they are skew lines, so they do not intersect, so you don't need to consider that. So you're talking about L1 and L2, and then we've got to have a similar approach to what we've just done. You pick a point on L1 and express it in terms of a general vector of L1, and pick a point on L2 again in terms of a general form of a straight line, and then you find AB. So we need AB first of all. So it's going to be OB minus OA. And OB, it's the point, so just have room to write OB. It's going to be minus 1 plus 2 mu, 3 minus mu, minus 1 minus mu. So it's going to be minus 1 plus 2 mu, 3 minus 1 mu, minus 1 minus mu, minus, and point A is going to be this one, so it's 1 plus no lambda, 0 plus 1 lambda, 0 plus lambda. So this is going to be 1 minus 1 minus 2 plus 2 mu, and this one is going to be 3 minus mu minus lambda, minus 1 minus mu minus lambda. There you go. Now what do I know about this vector? Very similar to what we've just done. This vector is both perpendicular to L1 and L2, but I'm just going to do the first, this time I need to do both dot products. So I'm going to do AB and I'll dot it together with D1, which is 0, 1, 1, and the answer should be 0. So AB is minus 2 plus 2 mu, 3 minus mu minus lambda, minus 1 minus mu minus lambda. Let's dot it together with the direction vector 0, 1, 1. That's of the line L1, because it's got to be perpendicular. So that will give me, that's just going to be 0. Then 1 times the second component, so plus 3 minus mu minus lambda, and then 1 times this one, so it's minus 1 minus mu minus lambda. That gives me the answer of 0. So if you put these two together, you're going to get minus 2 lambda minus 2 mu is equal to minus 2. So it's lambda plus mu is equal to 1. That's the first equation, which is quite nice. Now that has two unknowns, so I need to find another equation. So the other equation is, we're doing exactly the same but with a second line, because it has to be perpendicular to the other line. So I didn't need to do it twice in the other way, because it's they were both lines were parallel, so I just needed to do it to one of them only. So this here is going to be exactly the same situation, except my D2 is going to be different. So these can potentially be quite messy, so please take care when working with these. We just happen to have a nice vector over here. This one is not so nice. 2 minus 1 minus 1. So what have we got there? So you've got two lots of the first entry, so it's going to be minus 4 plus 4 mu. Add minus 1 times this, so it's minus 3 plus mu plus lambda. And then the same, minus 1 times this, that's actually not too bad, plus 1 plus mu plus lambda, and that has to be equal to 0 because the dot product is 0. So how many lambdas have we got? 2 lambda. We've got 4, 5, 6 mu's, and then minus 7 plus 1, which is minus 6, so it's 6 on the other side, So it's lambda plus 3 mu is equal to 3. So you've got equation 1 star, equation 2 star, there you go. Or maybe I and I. Okay, so let's solve them together. Let's put the first equation here. I'm going to just eliminate it. Subtract, you'll get 2 mu is equal to 2. Mu is equal to 1. So lambda has to be equal to 0. That works nicely. Okay, so how do I find what the distance is? So the distance is going to be my AB, the modulus of AB. So remember, AB was over here. So this is minus 2 plus 2 mu, 3 minus mu minus lambda, minus 1 minus mu minus lambda. So mu is equal to 1, lambda is equal to 0. So that gives me minus 2 plus 2, so it's 0. Minus 3 minus, that's 2. And then minus and minus plus 0, so it's minus 2. So modulus of AB is equal to 0 squared plus 2 squared plus 2 squared square root of, which is 2 root 2. Excellent. Example 26. So in this example, you've got equation of a line. So you've got a straight line L. We need to rewrite this equation so we can identify the direction vector of this line very easily. So in this case, it's going to be R equals, and we're going to have a point which is 1, 1, minus 3, plus lambda, and the direction vector is 2, minus 2, minus 1. So the way to do it, as we are looking for the shortest distance from point A with the coordinates 1, 2, minus 1 to the straight line, we know that we're looking for the length of this line. It makes a right angle with our straight line. So we're going to find the vector from the point A to the line, and then we're going to do the dot product with the direction vector of that line. So I'm just going to jot down the direction vector. So a general point of that on that line is simply 1 plus 2 lambda, 1 minus 2 lambda, and minus 3 minus lambda. So there is a lambda that will take you to that point. And that's what we are going to try and find out. So let's find the vector. Let's call that AX. So I've got the name of that, or XA, it doesn't really matter. So we're going to go for AX. So it's going to be end minus the beginning. So it's OX minus OA. So it's 1 plus 2 lambda, 1 minus 2 lambda, and minus 3 minus lambda. Subtract 1, 2, minus 1. Okay, so you're going to get 2a minus 2a minus 1. Sorry, minus 2 lambda minus a, 2 lambda, not 2a. And minus lambda. This one is going to be minus 3 plus 1, so it's minus 2. Let me just double check. Yeah, that looks good. Okay, so this is our vector OA. AX, actually, I found out. It doesn't matter, you could have done XA as well. So AX dotted together with the direction vector, that needs to be equal to 0. So 2 lambda minus 2 lambda minus 1 minus lambda minus 2 dotted together with 2 minus 2 minus 1 must be 0. So what do we get? We get 4 lambda. We're going to get plus 4 lambda plus 2 when you multiply these components, and plus lambda plus 2. And that's going to be equal to 0. So we've got 9 lambda is equal to minus 4, giving me lambda is minus 4/9. Okay, so what is the length of AX? That's what we're looking for. So we're going to sub minus 4/9 into this vector over here. So minus 2 times minus 4/9 minus 1. And then minus 4/9 minus 2. So it's going to be minus 8/9 minus 1 is going to be minus 1/9, and then 4/9 minus, so it's going to be minus 14/9. Okay, so let's do the Pythagoras. 8/9 squared plus 1/9 squared plus 14/9 squared. That will come up to 64, 65, 196. So it's 261. Put it in the calculator and you will get root 29/3. Change it to a decimal if you wish. Probably a good idea to do that. Okay, so this is example 26. Okay, the next section is deals with perpendicular distance from a point to plane. Well, the formula is actually in the formula booklet, so we'll talk about it in a second. Before we do that, there is a very important key result, which looks in the following way. So if you were to write an equation of a plane and the normal vector that you are using is a unit vector, so a vector of length 1, then the value you get at the end, so that value k here, this represents the distance from the plane to the origin. So remember, the unit vector is your vector divided by its length. So for example, if I had the following equation of a plane, so let's have 2x minus y minus 2z is equal to 4, for example. Then if the normal vector is 2 minus 1 minus 2, but the unit vector, so this is the normal vector, but the unit vector in that direction, which is written like this, n with a hat, is simply that vector divided by its length. So it's going to be, the length is 2 squared plus 1 squared plus 2 squared square rooted, which will be 3, I think, over minus 2 minus 1 minus, sorry, plus 2 minus 1 minus 2. So it's going to be 2/3, because we're dividing by 3, minus 1/3 minus 2/3. So we've divided our vector by 3. So if we were to divide all of that by 3, this equation by 3, the number you're going to get on the right hand side should represent the distance from the plane to the origin. So let's just show you what it would look like. So you would have 2/3 of x minus 1/3 of y minus 2/3 of z is equal to 4/3. So k is equal to 4/3. in this particular instance. Okay, so that is quite an important result. Now, the formula, which actually, if you follow logically what we've just said and apply it to a distance from a point to the plane, has been condensed into this formula. We're not going to prove it, but it is possible to prove it nicely. There is the plane ax plus by plus cz is equal to d, and we are going to look at the point with the coordinates alpha, beta, gamma. Then the distance from of that point to the plane is equal to a alpha plus b beta plus c gamma minus d over the length of that normal. So you literally substitute the coordinates of that point into the equation of the plane. You take away the value, so that's on the right hand side, so minus d, and you divide it by the length of that vector a, b, c. Okay, so let's see if we can apply this formula into the next example. I think it must be in here. Apologies. Okay, example 27. So we've got to find the distance from the point 3 to minus 1 to that plane. So you can sketch it if you want to, but really the idea is to quote the formula from the formula booklet. So distance, that's going to be equal to a alpha. You need to put the modulus in case that expression evaluated at that point in the numerator is going to turn out negative. So you need to talk about distance, so you need to change it into positive. There you go. So our a is 2 alpha, beta, gamma is the coordinates of the point, and a, b, c are the normal vectors, I, j, and k components of the normal vector. They call it d here. There you go. Okay, so it's going to be 2 times 3 minus 3 times 2 plus 1 times minus 1 minus 5, almost forgot minus 5, over 2 squared plus 3 squared plus 1 squared. Okay, so that's going to be 6 minus 6 minus 1 minus 5, so it's modulus of minus 6 over 4, 9, and 1, so it's square root of 14. So it's 6 over root 14, or 6/14 over 14. Okay, so example 28, here's the plane pi r dotted with 1, 2, 2 is equal to 5, and here are the coordinates of the point. We've got to find the shortest distance, so I'm not going to rewrite that, just going to use that straight away. Shortest distance, so I'm literally dotting together these this point with the normal vector to obtain this first 3 parts of the numerator. So it's going to be 1 times 1 plus 2 times 3 plus 2 times minus 2, and then minus 5 over 1 squared plus 2 squared plus 2 squared square rooted. So it's 1 plus 6, which is 7, minus 4, which is 3, and minus 5. I'm just minus 9. That's right, minus 2. And then here we are going to have 3. So it's 2/3. Part B, we've got to find coordinates of point Q, which is a reflection of point P in our plane, we've got to find it. So let's just sketch the picture. So here's my plane, pi. Here is a point which we called 1, 3, minus 2, point P, 1, 3, minus 2. Okay, so we're going to imagine that point. Shortest distance has been found, and there is a point Q that you obtain by reflecting this point in the plane. So remember, in order to find the position of that vector, this reflection needs to be happening along the normal line passing through P. So let's find the equation of that line. So we need a line PQ. Okay, so let's find that line. So it's going to be r is equal to 1, 3, minus 2 plus lambda, and let's use the direction vector of the normal 1, 2, 2. We take it from the equation of the plane. There you go. So what do I know? I know that this point here is on that normal line, that line LPQ, and also on pi. Let me just write pi. Pi was x. Well, let's just write it like this: r dotted with 1, 2, 2 equals 5. Okay, so in order to find the position vector of that point, so find the point of intersection. So we need point of intersection with pi. So what we're going to do is to substitute the general point of the straight line into the plane. So 1 plus lambda is that point, 3 plus 2 lambda, minus 2 plus 2 lambda. Let's dot it together with the plane. There you go. So it's going to be 1 plus lambda plus times that by 2 is 6 plus 4 lambda times this one by 2 is minus 4 plus 4 lambda is equal to 5. So we've got 9 lambda, and you've got 1 plus 6, which is 7, minus 4, which is 3. And then on the other side, it's going to give me 2. Let's just double check. So that will be 9, take away 7, that will give me 2. Okay, so lambda is equal to 2/9. So that will give me the position vector of that point. So that will be 1 plus 2/9, 3 plus 2 times 2/9, minus 2 plus 2 times 2/9, which is 11/9. This one is going to be 3 times 9, which is 27 plus 4, 31/9. And this one is going to be minus 18 plus 4, so it's minus 14/9. Okay, so it's 11/9, 31/9, and minus 14/9. So that was this point here. Let's call that point A, actually. Right, so how are we going to find the position vector of point P? Well, it's just simply, if you've got PA, vector PA added to A to get to Q, that's one way of doing it. You could just do PA and times it by 2 and add it to position vector of P. That's another way of doing it. So we're going to go, I'm going to go from OA, and I'm going to add PA to that. So OA we've got written here. PA is however long it takes me from 1 to 11 ninths. So from 1 to 11 ninths, it's going to be 2 ninths if you take it away. From 3 to 31 ninths, so from 27 to 31 ninths, that's going to be 4 ninths. And from -2, which is -18, down to -14 is 4 ninths. There you go. So let's add these two together. So it's going to be 11 ninths plus 2 ninths. That will take me to 13 ninths. 31 plus 4 is going to be 35 ninths. And -14 plus 4 is -10 ninths. So this is our position vector of Q, which gives me 13 ninths, 35 ninths, -10 ninths. That's the final answer. Example 29, here we've got a straight line L1 and plane pi, and we've got to find the equation of the line that you obtain by reflecting L1 in plane pi. So if you imagine there's your plane, and there is just draw it like that actually. If this is L1, then we're looking for a line that you obtain by reflecting that line in the plane pi. So this is L2, and what you are effectively seeking here, if you look at this, let me just draw it again. So this angle here needs to be the same as this angle over here. So this is going to be a right angle. So if you imagine picking a point on that line, there will be another point that is going to be a reflection of that point in that plane, and it will be over here. So let's just put all those ideas together. So let's call that point P and that point Q. And that point A maybe, and that, if we needed, point M for midpoint between P and Q. Right, so what do we know? Let's actually pick a point. Any point on L1 will do. Let's just rewrite L1 in its vector form. So R is equal to 2, 4 minus 6 plus lambda, and you've got 2 minus 2, 1. So let's, since we know that 2, 4 minus 6 is on that line, let's use this one. So it's 2, 4 minus 6, why not? Okay, so there is a point on L2 that's reflected in the plane. So what can we find out? So if we can find that point Q, and then if we can find point A, we should be able to find the equation of L2. So we need P, we need Q, and we need A. There you go. So let's start with Q. Okay, to find Q, we are going to find the equation of the line that's perpendicular to the plane and passes through P, M, and Q. So let's call that line, I don't know, line L3. So R is equal to, it's going to be point, which is point P, 2, 4 minus 6, plus mu, and the normal is the normal to the plane. So it's 2 minus 3, 1. So my point M or Q really, this can be written in terms of a general point on the line. We're going to find M. We're going to find a point of intersection between L3 and pi. There you go. So let's substitute the general point on the line. So 2 plus 2 mu, 4 minus 3 mu, and minus 6 plus 1 mu. And we are going to substitute this point into the equation of the plane. So you're going to get 2 times 2 plus 2 mu minus 3 times 4 minus 3 mu plus minus 6 plus mu is equal to 8. So let's work it out. This is going to be 4 mu plus 9 mu, which is 13 mu plus 1 mu, 14 mu. And then we have 4 minus 12, which is minus 8, minus 6, which is minus 14. On this side becomes 14 plus 8 is going to be 22. So mu is equal to 22 over 14, 11 over 7. So point M, OM, let's do the position vector of M. This is going to be 2 plus 2 times 11 sevenths, 4 minus 3 plus 11 sevenths. I'm substituting it into the equation that's perpendicular to the plane. So this is going to be 14 plus 22, so it's 36 over 7. This is going to be 28 minus 33, which is minus 5 sevenths. And this is going to be minus 42 plus 11, so it's minus 31 sevenths. So this is the position vector of point M. Okay, so now to find Q, let's write this one down here. 36 sevenths minus 5 sevenths and minus 31 sevenths. So let's find Q. So OQ, how you do it, it's your choice. You can, again, you've got the equation of a straight line, which is, we called it L3. So from P to M, you're going to go from 2 to 36 sevenths. That was 14. Take it away from 36, so it's 22 sevenths, which was here. So 22 sevenths. Then you've got minus 33 sevenths and then 11 sevenths. Let me just double check. From 4 to minus 5 sevenths, so that's 28 to minus 28 sevenths down to minus 5 is minus 33. And just double check, minus 48 up to minus 31 is 11. That's fine. So we are going to add this vector to our point OM, or you can do 2 lots of this vector to get to add it to point P. But I'm going, what did I say I was going to do? OQ, I was going to add this vector to the position vector of point M. Really, it's up to you how you do it. There's lots of options here. So 22 plus 36, that will be 58 sevenths. Minus 33 and minus 5 is minus 38 sevenths. And then 11 minus 31, that's minus 20 sevenths. So this is our point Q. Now we need to find point A. So we also need to find the point of intersection of the line L1 with the plane, so point A. So we need to substitute the general point of the line L1 into the plane. So for point A, we are going to use general equation of the L1, which is 2 plus 2 lambda, 4 minus 2 lambda minus 6 plus lambda, and we are going to substitute it into our plane 2x minus 3y plus z equals 8. So 2 multiplied by 2 plus 2 lambda, minus 3 is 4 minus 2 lambda, plus minus 6 plus lambda is equal to 8. So it's 4 plus 4 lambda minus 12 plus 6 lambda minus 6 plus lambda is equal to 8. So what have we got? We've got 11 lambda, and it's 4 minus 12 minus 6, so it's going to be minus 8, and minus 14 on the other side. It's going to be 22. That's a nice number. 22 over 11 is 2. So point A, the position vector of point A is going to be 2 plus 2 lambdas, 4 minus 2 lambdas, minus 6 plus 1 lambda, and the lambda is equal to 2. So it's going to be 6, 0, minus 4. So now we've got point A, which is 6, 0, minus 4. We've got point Q from the previous part, which is very awkward, 58 over 7, minus 38 over 7, minus 20 over 7. And we're going to find the line L2, which is through A and Q. So let's use 6, 0, minus 4 as our point, plus lambda. Let's find the direction vector. Let's go for AQ. So it's going to be Q minus A, so it's 58 minus 42. You can do it on the calculator. So that's going to be 16 sevenths, then minus, well, I put it this way, minus 38 sevenths J, and then minus 20 to add, take away negative 28, so add 28 will give me 8 sevenths K. Just double check, minus 20 minus 28 minus 20 is plus 28. That's correct. So let's use the direction vector. You can scale it up. You can use these as 16 sevenths minus 38 sevenths plus 8 sevenths, or I'm going to scale it up, times it by 7, and that will work. And you can even then divide by 2 if you wish, but that's one of the possibilities. So this is the last example of chapter 9.